Okay, so we've been talking about probability, and we've been working on how to combine different kinds of probability. And today we want to go a little bit further in terms of formulas that are used for probability. Certainly it's worth a little bit of review here. To say that we basically have two different kinds of probability. That we have the kind that works with tree diagrams, and we also have the one which is called contingency tables. So, for example, let's say I have a general probability of people who like soccer. And let's say the probability that they like it would be 10%. And then if I say, what's the probability that I'm going to have two people who like soccer? If I ask two people, I should say, if I ask two people and they both like soccer, what would be that probability? Somebody tell me that. Yes, you should have your calculator out already, you know. And yes, you should be able to calculate this. 0.01. We multiply those two numbers together. If, however, I have something that looks like this, if I have a table, we're going to use this table a lot in the next few minutes. So let's say we have business majors and nursing majors. And let's talk about Coke and Pepsi and other. This is certainly relevant because of the Super Bowl, where they talk about, is it okay to have Pepsi? And the thrust of the advertisement was, it's more than okay, but that does depend on your opinion, right? So if you say, I do have a favorite, Coke or Pepsi or something else. So we're going to put some numbers in here. And we should probably change this. We'll make this 40 here. Make this 10. And that's going to be 80. So okay, I gotta make this work now. Oh, I guess I'm gonna have to change it up a little bit. So let's go with this. There we go. All right, so here I have numbers for business students versus nursing students. For Coke, it's 40 to 20. For Pepsi, it's 30 to 10. And for other, it's 10 to 10. So if I ask the question, what is the probability of being a nursing student and a Coke drinker? know how to get that number. Talked about this a little bit previously. So let's see if we can make this happen here. And if I ask you a question and you prefer not to answer, you can just pass. That's not a problem. My goal is to just get you involved in the process here. Okay? So, Jaron, can you tell me how to find that out?
For the nurse and Coke,
I want someone who is a nursing student and they like Coke.
then you would look at your charts. So then that would be, Coke and nurse would be 20 over the sum of the whole table.
Okay, that's correct. So we're looking at the nursing and Coke, and that is this number 20 because that's where they are both true. So I need to know how many people are in the whole table.
120.
120. So let's do a percent right there to the nearest percent. I want to know what that number is.
16.6%.
I want it to the nearest percent.
17%.
So that's 17%. Okay. Notice that I did not use a formula in the sense of actually multiplying anything. I just looked at who's in the category divided by the total. Okay? So, when we have something like this first situation, when we're talking about a tree diagram, when we're just asking the question, yes or no, do you like soccer? And the probability is 0.10. And then we ask the next person, and that probability is also 0.10. Then that's what this is, multiplying the two together. That gives us and. When we have two events that are separated like this, when we're talking about the tree diagram. But over here, we are not multiplying two probabilities together in order to get this number. Okay. Now, if we were to ask the question, what is the probability that I have a person who likes soccer or does not? I want to include both possibilities. Either they like soccer or they don't.
That would just be 100%.
It would just be 100% because those are the only two things that can possibly happen. And I want to include all those possibilities. So that would just be 100%. Either they do or they don't. Now, what we're talking about here, there is a definition of this which is called mutually exclusive. What does it mean to be mutually exclusive? It means that there is nothing in common. And we normally think about things this way. Either you say, I like soccer, or you say, I don't. There's only two possible things. There's no middle ground in there where you say, well, I kind of do, but I kind of don't. We're not allowing people to answer that way. Over here, if we were to say, what's the probability of someone liking Coke or Pepsi? What would we have in this sense? What would we be talking about? It means I want to include all the people who like Coke, and I also want to include all the people that like Pepsi. All right? Jeff, what would you think of doing with this here?
You take the total of Coke drinkers for both the business and the nurse,
Okay,
And you take the total of the Pepsi drinkers, which would be for business and nurse, and then you divide that by the total, which is 120.
okay, so then how many total people am I looking at for the Coke or Pepsi?
100.
Okay, so this would be 100 over 120. Now, there are people who are in the other category, doesn't include them, but we would just be adding together all these different things. So then this would actually be the probability of someone liking Coke plus the probability of someone liking Pepsi. This works, this is the correct thing, because these are mutually exclusive, once again. There's no overlap here. Since there's no overlap between the categories, we can simply add the probabilities together when we're talking about or. However, that's not always the case. What would be the probability of being a Coke drinker or a nursing student? So we talked about this previously. So hopefully it's in there somewhere. Cam, can you tell me what's the probability of Coke or nursing? How would you go about figuring that out?
You're gonna see all the people that are Coke drinkers and not nurses, and all the nurses that are Coke drinkers.
Not exactly. It's related, but it's not exactly what I want. Dylan, can you tell me?
Pass.
Okay. So I'll let you know how this works. In order for you to know the Coke or the nursing, we have to include all the people that drink Coke. We also have to include all the people that are in nursing. We have to be careful, though, that we don't double count people in the overlapping part. So what we would have here then, if we take all the people who want Coke, that would be the 60 here. This is 40 and this is 20. And this comes out to be 80 and 40. So if we say Coke or nursing, then we would have 60 people who like Coke plus 80 people who are in nursing. But then we have to subtract the 40 people who would be double counted. So we want everyone in this row. We also want everyone in this column. So if I just take 80 plus 60, I would have to subtract the 40 because that's not part of it. Another way to think about it would be, I want these 4 squares or cells. And so I would just add those 4 things up. I would add all of these, and then I would have to add these people who are.
Rick, you want nursing, not
Yeah, are we pointing at the right column?
Oh, I was doing business. Thank you. Scratch that off. I want Coke, which is 60, plus the 40, minus the 20. That's better. Thank you. So then this would be all the people in this second column, all the nurses, all the people in this first row, the Coke drinkers. But I don't want to double count these 20 people. So if I take 60 plus 40, I'd have to subtract 20 out of there. So this would be 80 over 120. Or I could simply add all the people in the nursing column and then just add the ones here, which are not in that column, but they are still Coke. Either way, it doesn't matter, as long as you're able to get that right answer. So then, when we look at this process, once again, we are combining probabilities, but this is what that would look like. This would be the probability of Coke plus the probability of nursing minus the probability of coke and nursing. And we talked about this. This was the general formula for OR. And it's used when we have situations where they are not mutually exclusive. Mutually exclusive means they're completely separate. These are not completely separate. Okay. Now, the concept of mutually exclusive is relatively simple unless you don't actually know what it means. If you don't know what mutually exclusive is, then you're kind of lost. But the words mutually exclusive just mean that there's nothing in common between the categories. If they have something in common, they are not mutually exclusive. A lot of people think that's really important and think that's a good thing to know. The fact is, it's not that big of a deal because you can just look and you can see, do they overlap or do they not? There's another concept, a different concept, which is very important in statistics, which is used all the time, which is constantly being put in the public as saying this is really important. So this is the thing that you really need to know, and it is the concept of being independent, which is not the same thing as mutually exclusive. Okay? So what we're going to talk about are two things: conditional probability and independence. And we're looking at our chart here, not at the tree. What is conditional probability? Conditional probability, in the description of it, it's when we decrease our sample to a specific category. So instead of talking about everybody in our group that we observed, we're going to take just a category and we're going to consider from that smaller group what we can say. So this is how it's done. What's the probability of being a nursing student given that you are a Coke drinker? This line right here, we use the word given. And what it means is that whatever comes after that line, this is our new total. So instead of saying I'm looking at these entire 120 people, I'm now only looking at the Coke drinkers. So then I say, out of the 60, how many of them are nursing students? Well, it's 20. 20 out of 60, which would be 33%. Now, when you see this, hopefully you can get something in mind here. What I want to know is, how do these categories affect these percentages? Is there something that happens when I divide people up into these different categories? And so what I'm going to compare this to is just the probability of being a nursing student. Out of all the people that I chose, how many of them were nursing students? Well, that would be 40 out of 120, which is also 33%. So we've established this pattern here. The Coke drinkers are 30% or 33% nursing students, and the entire sample is also 33% nursing students. This is what we call independent. What does that mean, independent? It means that the categories do not affect the proportions or the percentages. We walk into the room of all these people and we say, hey, how many nursing students do we have? 33%. Okay. Then we say, okay, I'm going to put the Coke drinkers over here. All right. How many of you are nursing students? 33%. So it didn't matter. Putting them in the category did not change the percentages. So that means nursing students and Coke drinkers are independent of each other. So now let's do a contrast. What is the probability of being a nursing student given that you're a Pepsi drinker? So when we look at the Pepsi drinkers, now we're only looking at those 40 people, and we say the nursing would be 10 out of that amount. So that's 10 out of 40. What just happened? Our proportion has changed. This is 25%. So now this is called dependent. Hopefully you can see the category does affect the proportions. If I look at this and I say, Coke drinkers, it's 33%. It doesn't matter what category you're in. Or, I'm sorry, nursing students. Nursing students are 33% if you're a Coke drinker or if you're not. But when I look at Pepsi drinkers, it's changed. The proportion of nursing students is lower. So it looks to me like taking Pepsi drinkers, there are not as many nursing students. So that would tend to indicate Pepsi is not the favorite or as favored by the nursing students because this changed, it's lower. This is everything in social media. This is everything for Google, Amazon, everybody. All the advertisement that ever happens. This is all insurance right here. This is all of our new culture where we find things out by looking for them on the computer. Because we say somehow, if you're interested in this, you are more likely to be interested in that. And so because of that, you're going to have our ads that are targeted to you because of your interest. And they're going to put that in there because they want to make money from people who have a better chance of buying the thing. They don't want to advertise flowers to people who don't care about flowers. They want to advertise flowers to those people who they think are going to buy them. And so if it's like, okay, well, I'm doing some wedding planning. Boom, all of a sudden, you're getting hit with all these ads for wedding stuff, including flowers. But in your just normal day, you don't see an ad for flowers because you're not part of that group that got affected by that category. People who are interested in weddings are going to be more interested in, make a nice long list of those things. Scott.
Why wouldn't you want to bring up your dependents as an advertiser? Why wouldn't you want to bring up the lower percentage?
It's possible that you would say, there's a bunch of people out there who don't want flowers. I want to persuade them that they do want flowers. so that I can get more business from people who don't normally buy my thing.
If it's already 33% for Coke, regardless of whether it's a nurse or just in general, then why wouldn't I want to try and pick up on the people that aren't?
Well, see, as an advertiser, you can have different goals. You can say, I want to persuade people who have never heard of my product that they should have my product. But that means I need to let them know. I need to give them information, right? Same kind of thing here. If I say, let's just use me as an example. I never buy flowers. Why wouldn't they try to hit me with flower ads to get me to buy flowers? They could, but if you're going to say, I would prefer as a business to target people that I know are going to buy something like my product, so then I can say, oh, well, it's the best option for you because you're interested in it. It's like, I could try to persuade people who don't want my stuff, but it seems easier for me to persuade people who want something like my stuff to actually get mine. And so then, in terms of persuasion, it does happen. It is out there where people will say, you don't know that you need this. And so I'm going to tell you that you do. And there is advertisement that goes to that point. But there's just a ton more of people who say, oh, you want this thing that's green? Well, here, the other thing is also green. You like green, right? So it tends to be easier for people to make the sale when somebody's almost buying the thing that's pretty close to it.
Okay.
Not to say that doesn't happen. It's just that the other stuff just happens a whole heck of a lot more. Now, let's talk medication. You're going to give a bunch of people a particular compound that you made, and you want them to get better from a particular thing. What are you going to have to do? You're going to have to prove that the people who took the stuff get better more than the people who don't. You take this, you'll feel better. What does that really mean? The percentage is higher than it would be otherwise. Well, how much higher? And who's measuring? And how do we decide if somebody's going to be willing to pay for that or not? Well, that's a big question, right? Let's say you've got somebody who needs a stent for a heart bypass. And you're like, well, you know, if you don't have this, you're not going to live very long. All right, I'll pay the $10,000 or whatever. And then I'll live longer. Okay. Well, here's this particular pill that you need to take because you're drinking too much soda. It's affecting your blood chemistry. And you take this pill, and it'll be $10,000 for you to take this pill to make your chemistry better. Well, why don't I just stop drinking soda? That'd be a better option instead of spending $10,000 for a pill that reverses the effect. Well, yeah, but we can't advertise that. It won't give us any money. Well, sorry, I'm just going to stop doing this thing. Well, but then somebody says, well, I'd prefer to have a pill than to give up this other thing over here. Oh, well, there's a market then. Sure. But it's based on these percentages. What happens when somebody takes a medicine? Does it change anything? Or what does it change and how much? This is how we decide. So in the situation when we say independent things, the categories do not affect the proportions. Dependent is a situation the categories do affect the proportions. So if we want a formula for that, then we want the probability of A is equal to the probability of A given B. This then would be independence. Independence says that the probability of something happening is the same if you consider it from a subcategory or if you don't. Either way, they are the same. That's independence. So this is how you show independence. You have this. Okay? Now, if I say what is another way to do this formula, this conditional probability. Another way I can do that is to say the probability of A given B is the probability of A and B over the probability of B itself. Notice how this worked. When I said, what's the probability of nursing given Pepsi? I had the nursing and Pepsi divided by the Pepsi. So I could have said this was 10, pardon me, 10 over 120 over 40 over 120. That's the same as 10 over 40. So I can either look at the number of people in those categories, or I can use probability numbers. So this formula, pardon me, this formula also works. So, now this is not the easy part, but this is what happens. Probability of B multiplied by the probability of A given B equals the probability of A and B. Notice what I did there, I just multiplied both sides of the equation by probability of B. This is the general multiplication rule. It is true, when you multiply, this does work. Notice this is a little bit different from if I have independent events, this works. This is for independent events. We already know this formula because we used it for the tree diagram. We said if you have a tree diagram, you multiply the probabilities together and it gets the probability of the things both happening. So, in your homework, what you'll find is a bunch of stuff about these formulas. That if you know the probability of A and B, and you know this probability, you can find the other one. So you can put things in here, in these formulas, and find the other ones missing. But I don't want you to lose sight of the major concept here. The major concept is the definition of what it means to be independent. If it's independent, then it doesn't matter what category you put people in. It's still, their percentages are the same. But if they're dependent, then it changes it. That's what we want to find out. We want to find out, for example, is it the case that if someone is under 25, that they have a higher risk of accidental injuries? Well, we would figure out what are all the risks of accidental injuries, and then we would separate out the category and see if those proportions change. That's what we want to know. That's how we're going to find it out. We're going to separate those things. So then that's another part of the homework, is to go through and kind of describe those situations where you have something where someone is in a particular category. Does that mean they're going to have a higher or lower chance of something. All right, so let's do one other thing, and then maybe we'll come back to this. All right, let's get rid of this. The other thing I want us to consider is something called counting rules. We've mentioned this in the past about how do we know the number of possibilities that exist. And specifically, if we say, I'm going to pick 4 people out of 10. Okay. Then we have 2 possibilities. The first one will be that the order is important. And the second one would be, no, it's not. That the order doesn't matter. The most common situation when we talk about probability, okay, when we're talking about actually counting the things that happen, the order is actually important. If I say I pick this person and then I pick a different one, then in terms of just listing all the options, it is important to say that's a different event. If things happen in a different order, it is a separate event. I mean, you'll know this, right? If you put on your socks and then your shoes, that's a lot different than putting on your shoes and then your socks. It is. It's just a different thing. Now, when we do that then, what we're talking about here is called a permutation. Because a permutation says if I switch the order, that's a different thing. So then, if I pick 4 people out of 10, the way that this is written is the number 10, a capital P, and then the number 4, both as subscripts. So this is 10P4. Now, if you have access to your calculator right now, it might be good for you to find this on your calculator. How do I know what 10P4 is? Well, you got some kind of a menu or a button or a probability thing that's out there somewhere. And usually you'd have to put in the 10, then push a button, and then hit the 4, and you get a number. And then the question is, what number do you get? Megan, did you get something out there? No. Okay. Josiah, do you got anything?
0.03.
It is not. No. Nope. I need 10P4. Ake, you got something?
Yeah, 5,040.
5,040. Okay. That's the number. So if your calculator is not able to do this, the software out there certainly is. Okay. If you put that, I mean, you could try just Googling it, or if you have a favorite algebra website or something, or if you have, bless you, if you have a spreadsheet, spreadsheets will do this. You just have to look up how to do permutations. And there's information in the textbook about how to use the software. But this is it then. if I'm going to pick 4 people out of 10, this is how many possible arrangements that there are. Now, there is a formula for this. It's not absolutely necessary that you know the formula, which would be, I'm pretty sure, n factorial over x factorial. Or is it n minus x? Oh, I don't remember. Like I said, I don't really pay attention to these things anyway. So if we go there, there it is. Yep, n minus x. N factorial meaning 10 times 9 times 8 and so on. And we've talked about this also. If I am taking 10 people and I take 1 out, I have 9 left. So then I would take 1 from the 9 and so on. So it's 4 choices each time, 1 fewer people. So then I have the 10 factorial, but I take off the other 6 out here and I left with 4. Now, this is useful for us to know, but then it's also useful for us to say, what if it doesn't matter the order? If I'm out there and I'm just picking people and I just want a group of 4 people, I don't care what the order is. Well, then what we have to do is combine our permutations, because then we say, I have this list of 5,040 things. I want to combine all of them that have the same 4 people. I want to put those together, and then that will give me a smaller number of different things that can happen. So then, when I talk about combinations, that would be 10C4. It's not the same thing as 10P4. So what's 10C for?
$210.
210. That would be 10 factorial over 4 factorial, 6 factorial. So this would be 10, 9, 8, 7 over 4, 3, 2, 1. Yep, 210. Now, this information will be helpful to us, but it's not, how should I say this? It's not exactly algebraically important in my mind, okay? Because you can just find out what these numbers are and put them in there. To say, well, which situation are you doing? Are you picking where the order is important or it's not? Fact of it is, most people never come up to those situations. So it's like, oh, well, in the larger world of statistics, these things don't matter as much as working with actual data numbers. So even though I reference this, it's not that big of a deal. So what I want you to be able to do is to recognize that there are 2 kinds of numbers and to be able to find them using your calculator or computer or something so that you can actually make that work. Other than that, it's not that big of a deal. Certainly, ideas about independence are much more important than just about anything else that we're going to do in the course. So you really need to understand what independence is and how it works, because that's going to come at us all the time as we go through our stuff. Okay?